Everyone, welcome back to another physics video. Today we'll be talking about representing motion using kinematic equations. So these are the three big kinematic equations that you'll see in physics. So a few things about these. The first thing is they only apply for constant acceleration, which means the acceleration must be constant. It cannot be changing, otherwise these will not be able to be used. Another thing is that these equations are all given in the x direction right now, but they can also just be applied in the y direction. For example, this equation could be the y position final minus y initial plus the velocity initial in the y direction times time plus 1/2 the acceleration in the y direction, t squared. And something to note about the y direction is that the acceleration is going to be the acceleration due to gravity, because when you're if you're just in free fall, the acceleration is usually going to be the acceleration due to gravity. So we denote it as a g, which equals 9.8 meters per second squared on Earth. So if you're not given acceleration and something's in free motion in the air, the y acceleration is going to be this gravity here. Alright, so let's do a couple examples using these equations. Alright, so we have Bob is traveling at 60 meters per second due west and starts accelerating at 15 meters per second squared due west for 10 meters. What is Bob's final velocity and how long is he traveling for? Alright, so first thing I always recommend is start by listing out what we're given here. So we know he initially is traveling at 60 meters per second due west, so that's the velocity initial is 60 meters per second. And we know it's due west, so if we have our compass over here, we'll just draw it over here. Typically we'll use west as the negative since it's to the left. So we'll denote west as negative, and I'll just draw that over here. So we'll make this value a negative, and now from now on any west directions will be negative and east will be positive. We also know that he starts accelerating at 15 meters per second squared due west for 10 meters. So his acceleration is equal to 15 meters per second squared. And since that's also due west, we'll have in the negative direction. And then finally we're given that it's for 10 meters. So we know that the change, and we'll just use x here, is going to be 10 meters. But since he was traveling west, that change is also going to be west. So if we draw out, let's say, we'll just draw a quick picture here. We have Bob right here, and he's traveling 60 meters per second. This change in x that he travels is also going to be in that direction. So we will also have to use a negative sign here to denote that. And so we want to know what is the final velocity and what is the time, how long was he traveling for. Alright, so this is what we're given. What equations can we use to start solving this? So first off, I see that if we look back at the equations that we need to find the final velocity, right? So if we try to use this equation has time here, and we don't know time yet. And this one also has time, we're not given time, but this equation right here is not given time, and we can solve for final velocity. So that's probably going to be the one we want to use here for this first part. So we can write this out as velocity final squared equals velocity initial squared plus 2 acceleration, and it's written as x final minus x initial. But we know that this is just equal to the change in x, right? So this we already have this variable, and we have all these other variables. All these variables we all have, so we just need to solve for this velocity final right there. So if we take the square root of each side, we end up getting that the v final is equal to the square root of v naught squared plus 2a delta x. And this could also be a plus or minus here. Okay. So now that we have our variable we want on its own, we can go ahead and plug in values here. So the velocity final is equal to plus or minus the square root of the initial velocity, which is a negative 60 squared plus 2, the acceleration, which is negative 15, and the change in x, which is negative 10. And we go ahead and plug this in, and we will get a velocity final that is equal to 62.4 meters per second. And we see we have this plus or minus here, right? We have this plus or minus, but we don't know is this plus or minus, right? So we have to think back to what makes sense, right? What would make sense? Bob is traveling west. The acceleration is also west, so he's speeding up. It wouldn't make sense for the direction to be in the east, right? If he's traveling this way and then getting faster, his final velocity is also going to be in that direction, so we would use a negative sign to denote this. But when writing our final answer, we can drop the negative sign and just write due west. And that will give you your answer for the first part. Okay, but now we need to know how long was Bob traveling for. Well, now if we look back at our initial equations, now that we have this v final, we could use this first equation. We could also use the second equation. But if we were to use the second equation, we would have to use quadratic formula since we have these t squareds here. So this first equation will be much easier to use. So we can use this first equation of Vf is equal to V naught plus AT, and we want to solve for t. So we can subtract this, so Vf minus V naught equals AT. And if I just solve for t now, t is equal to Vf minus V naught over acceleration. So I'll scroll down a little bit. So now that we have this with the t separated out, we can plug in our values here. So the final velocity is a negative value as we determined before. That's why we need to determine it. And our initial is also a negative value, which is negative 60. And we divide this by a negative acceleration of negative 15. And that will give us 0.163 seconds. So that's how long he was traveling for. So that's why it's important to keep track of your signs here, because if you mix up your signs, you will end up getting a different value. But if you were to choose positive for everything and make west positive, you would still get all the same answers. So if you wanted to try that on your own, you could do that. Alright, let's do one more example here. So we see Bob is on a 120 meter tall cliff and throws a ball straight up at 12 meters per second. What is the final velocity of the ball just before it reaches the ground? Alright. So again, let's start out by listing what variables are we given. So we know the initial velocity, v naught, is equal to 12 meters per second. And since he's throwing the ball upwards, we're going to leave this as a positive 12 meters per second. And we'll know up is positive and down is negative. Okay? We know that the cliff is 120 meters tall. So to make this a little clearer, I'm going to start by drawing my picture actually. So let's say we have a little cliff here that is 120 meters, right? The ball starts here and is thrown up at 12 meters per second, and it goes up, and then it comes all the way back down, and right before it hits the ground, it has some velocity final, and that's what we're trying to find, right? So when we want to know what is this 120 meter cliff, right? We can actually set the change in y equal to the 120 meters. And because it's starting at the 120 and ending at the very bottom, this will be a negative 120 because it's going down 120 meters. And notice that we don't care how high the ball gets when it's thrown up. We only care about this initial position and final position of the ball. So it's important that we don't care how high the ball goes because it's going to be thrown up higher than 120 before it falls. But we only care about the initial and final. Okay. So yeah, and we want to find the velocity final. That's what we're looking for. Now there's one more piece of information that we're not told, but we do have, and it's because we can assume we're on Earth here. So there will be an acceleration due to gravity in this y direction that's equal to a negative 9.8 meters per second squared. And gravity will always be negative because gravity is always going towards the Earth. Okay, so now I have to decide what equation do we want to use here. And again, if we look at them, we're looking for this velocity final, but we don't have time. We're going to use that same equation we used in the last problem. That is the v final squared equals the v initial squared plus, and then this time because it's in the y, we can say 2g delta y, because this is the change in x. This is acceleration. And we have all these variables now. We have enough information to solve it. So we can now go vf squared is, or not vf squared, but just vf is equal to the square root of v naught squared plus 2g delta y. And now that we have all of these variables, we can go ahead and plug them in. So vf is equal to the square root of v naught, which this is going in the positive direction. So it's 12 meters per second squared plus 2 and negative 9.8, and the change in y, which is 120. And this will also have a plus or minus on it, so the v final will be equal to 50 meters per second, right? And now we have to decide, is this a negative or positive? Well, when we draw our picture, the ball is going up, and then when it's coming down right before it's the ground, it's falling down towards the ground, so it'll be a negative right here, which means that our final answer will be 50 meters per second down, and that'll be our final answer. So always make sure you have the direction when you're solving for a vector value. Alright, that is it. Hope you all have a great one. See ya.